this chapter, which is the first part we are going to talk about, which is the nucleophilic substitution reaction. Nucleophilic substitution reaction. From its name, we have a nucleophile. A nucleophile will react with any alkyl halide, do you follow me? And then we will get a substitution reaction where the nucleophile will displace the halogen, and therefore we will have R nucleophile plus X nice. In this case, as you can see, that's why we call it nucleophilic substitution reaction. In all of these reactions, we have a nucleophile reacting with alkyl halide 2, and the nucleophile will displace the halogen, will substitute the halogen to get R nucleophile plus X. This is here called the nucleophile, as we have said before, and this is the substrate, this is the product, and the X here, which has been left the product, we call it leaving group. So that's the general reaction which we are going to discuss, which we are going to dedicate good amount of the time of this lecture. Now, how this reaction will take place? This reaction will take place in one of the two reaction mechanisms, or the mechanism of the reaction, either by SN1 or SN2. Nucleophilic substitution by 1 or nucleophilic substitution 2. The SN1 and SN2, these are actually the mechanisms which we are going now to explain the reaction or the reaction mechanism of this reaction. Let's start with SN2 reaction mechanism. Keeps moving. Alright, for the SN2, it's called bimolecular nucleophilic substitution reaction. Bimolecular nucleophilic substitution. Why we call it so? As you can see in the criteria and the characteristic of the SN2 reaction mechanisms, this is called actually the rate of this reaction. The rate is always depending on the Rx and the nucleophile. So this is first, yes please.
Camera is not work.
You cannot see, or what exactly the case?
Yes.
Is this for you or for everyone?
It is clear for me.
So then it's for the one who asked. Actually, you have a problem in your laptop. Please try to solve it. If someone can see, cannot be, someone can see, cannot, some others can't. Is there anyone else who has a problem with the camera?
Doctor, I see a part of the board.
You see a part of what? Of the board?
The left one. Can you move the camera?
You mean the board position is different than I cannot see. This is the case? Is this your posture?
Yes, doctor, it is fine.
Now it's clear. All right. Now, anyway, we said that's why actually we call it bimolecular substitution, nucleophilic substitution reaction. That the two here means the rate of the reaction depends on two molecules, which are the nucleophile concentration and the alkyl halide concentration. So this is the first characteristics, that the rate of the reaction depends on both concentrations of the nucleophile and as well as the alkyl substrate. All right? Okay. All right. Now, then second thing here, how the reaction take place. The reaction always, the second aspect or the second characteristic of the SN2 reaction, that the nucleophile attacks from the backside to the leaving group, and thus we will have something called inversion of configuration. First of all, let's just take the example and focus on it first from the beginning. Suppose we have this example. Suppose we have CH3, CH2, Br. Now, and then we allow it to react with OH minus, suppose. First of all, why do you think the OH minus will attack the carbon here, will react with this alkyl halide? Or where it will react? This OH minus, which atom it will attack? Which atom would like to react with? What do you think?
Maybe it will replace it Br.
Yes, of course, but I mean that means it will attack simply this carbon. Do you follow me? Why the nucleophile here will attack this carbon? Anyone knows? Why this carbon simply will be always accepting the nucleophile attack? The carbon which is attached to halogen always accepting or will be attacked by the nucleophile. Why? Anyone knows? All right. Because in principle, when you check the electronegativity between the halogen, any halogen, and the carbon, we will always find it, this is partial negative, this is partial positive. So it's very simple reason why. Because the nucleophile is always negative. Therefore, the nucleophile will attack always this carbon. And then the halogen here will leave with the electrons, and therefore we will have nucleophilic substitution reaction. Of course, we will get simply the CH3, CH2, then OH plus Br minus. Now, how the reaction will take place, I will just show you while sitting, just to maybe will be easier if I show to you. Let me just see myself first. If I can see myself. All right. Now, do you see? Can you see? This is a tetrahedral atom. This is a tetrahedral carbon in this case, as you can see. And imagine this is the nucleophile. You follow me? In principle, the nucleophile will attack from the backside. Suppose this is the halogen, which will leave. So the halogen here is in yellow color. So the best position for the nucleophile to attack this carbon, which is connected to the halogen, is to attack it from the backside. Do you follow me? Now, why do you think first the best position for the nucleophile to attack the carbon from the backside? Why it does not attack from this side? Anyone knows?
To avoid repulsion?
Absolutely. Because simply, as you can see here, the halogen here is very big, which means there are cloud of electrons, and the nucleophile, it's a negative charge. If it attacks from the same phase, there will be like repulsive forces. Therefore, to avoid repulsion, it will attack always from the backside. Do you follow me? So that's actually what's exactly going to happen. And in the transition state for this reaction, that the nucleophile attacks from the backside. So, but of course, as we know, the carbon is tetravalent. It can only be bonded to 4 atoms. In this transition state, as you can see, it looks like it is bonded to 5 bonds. So what's going to happen, this starts to bond with the carbon, and this bond with the halogen starts to break in order to go to, at the end of the day, the halogen will take the negative charge and go away. In other words, the transition state, what's going to happen for the mechanism, the SN2 mechanism reaction, we're talking about SN2 mechanism reaction. In the SN2 mechanism reaction, the carbon here will be connected to 3 atoms. Now the halogen here, which was, for example, here the Br, and the OH started to bond from the backward. So the OH will start to make a bond with the carbon, and the bond between the carbon and the Br start to break up. Do you follow me? As if actually the geometry of the transition state of the carbon in this case will be trigonal pi-pyramidal. If you remember this structure or this geometry, trigonal pi-pyramidal. This is the structure of the transition state of the carbon, transition of this reaction. You follow me? It will be trigonal pi-pyramidal. So after the reaction here, I want you just to focus about the stereochemistry. After the reaction took place, now imagine again that this is the OH, and the yellow atom here is the leaving group, which is in this case the halogen. Now when this attacks from here, this after the transition state, after the bonding complete and the disbonding complete, or the breaking of the bond complete, what's going to happen, this carbon will adopt the tetrahedral structure again. And this case, what's going to happen, you see this umbrella which was below, when this attacks from here, this umbrella becoming up, and therefore actually this looks like this actually. It's something like that. Do you follow me? So that's actually what we call it inversion of configuration. So we will have always SN2 reaction is accompanied with inversion of configuration. Inversion of configuration. In other words, if the carbon attached, if this carbon is chiral, suppose if this is R for any reason, the product here will be S. If this carbon is stereocenter for any, of course, not this example, but we will see some other examples. If this carbon is a stereocenter and its configuration is R, then the product will be always S because of this attack, because the attack of the nucleophile will always coming from the backside up to the halogen. Do you follow me? Is there any question so far?
دكتور
Yes, please.
إذا كانت الإلكترونيجاتيفيتي of النيوكليوفيليك أقل من اللي مرتبط في الرياكتنت هل بيصير تفاعل؟
دائما, always, whenever we have alkyl halide reacting with any nucleophile, the reaction will take place, regardless of anything else. Do you follow me? So, always, we will, of course, we will see some restrictions later on, but anyway, now for the time being, let's just focus on this. Any alkyl halide, when we allow any alkyl halide to react with a nucleophile, the reaction will go to R nucleophile plus X minus. That's most likely the case will be. You follow me? Slowly we will come to restrictions, to some limitations and so on and so forth, but we don't want to go now and discuss any limitations or any restrictions now. We will just assume that any nucleophile, when it reacts with alkyl halide, it will proceed like this way. And what we have discussed so far is the SN2 reaction mechanism. So as you can see, the SN2 reaction mechanism, it involves the attack of the nucleophile from the backside, and therefore we will have always inversion of configuration. I'll just write down the same example, what we have it in here, which is carbon attached to brom, methyl, and ethyl. Carbon attached to brom, methyl, and hydrogen, ethyl, hydrogen and ethyl, CH2, CH3. Now, when this reacts with, as the example actually, when this reacts with, when this reacts with OH minus, what's going to happen, as we said, that the OH will attack from this side, because we said actually always from the opposite side of the compound, and therefore what we are going to get, opposite configuration where we have it this way. So the ethyl is the same, CH2, CH3, then hydrogen, and then we'll have a methyl and a Br, methyl and OH, sorry. As I said, in the SN2 reaction mechanism, if this reaction to proceed from or via SN2 reaction mechanism, the nucleophile must attack from the backside. And if it attacks from the backside, this is the configuration what we are going to get. And what we are going to get, what we got in here, what we call it inversion of configuration. Inversion بالعربي, and what's the meaning of inversion? Configuration. What's the meaning of inversion? To invert something. يعني as if we are يعني زي كانوا معكوس عكس الconfiguration. فبالتالي so this here was the configuration of this stereocenter was R, and therefore we must get always S. So remember this all the time. Whenever you have a nucleophilic substitution reaction and it went via SN2 reaction mechanism, it must be accompanied with inversion of configuration, which means if we have a stereocenter in here, the configuration around the stereocenter will be inverted, and then we will get the enantiomer actually of that stereocenter. Clear so far? Is that clear, guys? Is there any question? All right. Now let's see here the order of reactivity. How the different alkyl halides react in this reaction mechanism. Which alkyl halide will react faster, and which one will be preferred more in this reaction mechanism? The rate of reaction, according to what you have it in here, we have methyl, primary, secondary, neopentyl, and tertiary. So if we have CH3Br, for example, this will be way much higher in reactivity compared to CH3CH2Br, and this will be higher in reactivity compared to CH3CH3Br, and this will be higher in reactivity compared to the neopentyl then CH3, then CH2Br, and this will be higher reactivity compared to CH3Br. Do you follow me? The difference is that the nature of the alkyl halide, this is methyl as we know, and alkyl halide. This is primary alkyl halide. This is secondary alkyl halide. This is tertiary alkyl halide. And this is special case, which we call it neopentyl. Neopentyl. Do you follow me? Now, the reason for this order of reactivity, or the variations of the order of the reactivity, I think it's very clear, because when we have, if you can see it in here, when we have these groups are very big size, then when this nucleophile comes from the backside, the reaction will be hindered, because there will be very much repulsive forces compared if these are hydrogens. If these are hydrogens, suppose like methyl alkyl halide, simply the nucleophile will face very less repulsive forces compared if these are R groups, such as methyl, ethyl, any other alkyl group in this case. So the reason for this order of the reactivity is simply because when we have more alkyl groups attached to the same carbon here, we will have hindrance of the reactivity, or simply here, as you can see, these bulk groups will hinder the nucleophile from attacking from the backside. Is that clear, guys? is the order of reactivity in SN2 reaction mechanism. Is it clear? And why we have such difference in reactivity? Is it clear? Is there any question? Is there any question?
No.
All right. Now, let's talk a little bit about the nucleophile. As you know, what's the nucleophile? What's our definition of any nucleophile? Anyone knows the definition of a nucleophile? What's a nucleophile? All right, let me define it again. A nucleophile is any negative charge. Do you follow me? Or, see, negative charge, very obvious that it is a nucleophile because it has excess of electrons. I think something wrong with the do you hear me, guys? Is there any problem in the I think there is a problem in the connection, isn't it? You can see, you can.
Yes.
So there is no problem in the connection? All right, perfect, okay, all right. Okay, now here the nucleophile is any negative charge or neutral molecule, as we said. But what's the condition? Contain and must contain lone pair or one atom contain an atom has or have lone pair has lone pair or pairs, lone pair. For example, H2O. H2O is a nucleophile, NH3 is a nucleophile, alcohol is a nucleophile. Do you follow me? Wherever we have a neutral molecule, you see this is a neutral molecules. All of these are neutral molecules. Whenever we have a neutral molecule where we have an atom contains lone pair or lone pairs, then in this case we will call it a nucleophile. And beside that, as we said, any negative ion, for example, Cl minus, Br minus, OH minus, Cl minus, any negative charge, any negative ion will be a nucleophile, isn't it? Do you follow me, guys? Keep talking to me just to know that you are following me nicely. Is it clear so far? This is here, as we said, the nucleophile, it can be any negative charge or neutral molecule. Negative charge, very obvious. Now the neutral molecule, not any neutral molecule is a nucleophile. Just a neutral molecule contain what? An atom which has what? A lone pair or lone pairs. Do you follow me? There must be an atom in this neutral molecule containing lone pair or lone pairs in order to be considered as neutral molecule, such as water or ammonia or alcohol or RNH2. Wherever we have an atom in the neutral molecule containing a lone pair or lone pairs, in this case we will consider it as a nucleophile. Clear? Is that clear?
Yes.
All right. Now, so what's happened? See, as you can see, we have two types of the nucleophile. What will happen when each type react in the nucleophilic substitution reaction? We will get the same result, the same final result, but with a little bit of variations. For example, here, if we have Rx, any alkyl halide, reacted with fully or negatively charged nucleophile, negative charge, negative nucleophile. Then in this case, the nucleophile will use its lone pairs to make a bond with the halogen, with the carbon here, and the lone pair, the bonding pairs here will be given to the X. Do you see this? That's what we are going to get. We are going to get Rx plus nucleophile minus. So we will get the final product directly. Now, imagine we allow the alkyl halide to react with a neutral nucleophile. And that's what the general formula of the neutral nucleophile. Before that, let's just give specific example. Here, suppose CH3Br plus OH minus. CH3Br plus OH minus, simply the OH minus will attack the CH3 and the bonding pairs here will be given to the Br. So we are going to get CH3OH plus Br minus. That's simply the case. Now, what if the nucleophile here, this is here in this case, the first case, where we have the nucleophile is negatively charged ion. Now, as we said, the nucleophile, yes?
How it's the reactant is the same as the product?
Would you please raise your voice and repeat your question?
How it's the reactant is the same as the product? You know, therefore, and above that Rx plus nucleophile, it's a reduced Rx plus nucleophile, it's the same.
No, of course not. It's just a type of mistake. Here it will be R nucleophile plus X minus. That's actually the reaction. Got it? Thank you. All right. Now here, as we said, the nucleophile, it can be two types. It can be negatively charged or neutral. So what will happen, how it will be different? It will be just slightly different. That first of all, the nucleophile, which has, for example, an atom with lone pairs, these lone pairs will be used to make a bond with the R, and the bonding pairs here, which was between the carbon and the halogen, will be given to the halogen. So what we are going to get, we are going to get R nucleophile, hydrogen, for example, and then it will carry a plus in this case, plus X minus. Do you follow me? Then, of course, the nucleophile here, since it has a hydrogen, in this case, the bonding electrons with the hydrogen here will be given back to the nucleophile, and then the hydrogen will be lost. So we are going to get finally R nucleophile plus H plus. Do you follow me? At the end of the day, it's either if we allow alkyl halide to react with a negatively charged nucleophile or neutral nucleophile, we are going to get the same product. For example, let's take a specific example in this case. The same here. If we allow CH3Br to react with water, which is simply the neutral nucleophile of the OH, can you see the difference between the two nucleophiles? This is negatively charged, this is neutral one. In this case, the first intermediate product will be CH3OH2 plus, because simply as such, this neutral nucleophile will be bonded to the carbon, and then the halogen will leave. And then, of course, plus Br minus. And then later on, the OH2 here, this compound here, one of the hydrogens, let me see, write it this way. One of the hydrogens which was attached to the oxygen will be simply lost, and the bonding pairs will be given to the oxygen, and then finally we are going to get CH3OH. So the same as we got in the neutral nucleophile. Clear, guys? Is that clear between? Is that clear between the difference between the reactivity of neutral nucleophile and negatively charged one? Is there any question? All right. Now let's see the next slide, which is about the nucleophile and the strength of the nucleophile. Now, generally speaking, as you can see in the nucleophile here, the strength of the nucleophile, you can see here we have different strength of the nucleophile or relative rate. You can check here the relative rate of these reactions in this table 11.1. You can see we have a different rate for the reactions. So when we compare, for example, water with acetate, with ammonia, with Cl minus, with OH minus, and so on. So we'll find different reactivity for the nucleophiles. Generally speaking, nucleophilicity actually is parallel to basicity. So that's why actually generally we have two trends for the nucleophilicity. How or when we can consider a nucleophile stronger than others. Let's talk about nucleophilicity. Nucleophilicity. The meaning of nucleophilicity which means the strength of the nucleophile. And which nucleophile is stronger, right? Generally speaking, there are two trends for the nucleophilicity based on the location of the atom in the periodic table. Generally, as we go down the group, nucleophilicity increases. بمعنى, if you compare the F minus with Cl minus, with Br minus, with I minus, which one is stronger nucleophile? As we go down, the nucleophile strength will be higher. Yani in this case, I minus will be higher or stronger as a nucleophile compared to Br minus, compared to Cl minus, compared to F minus. That's actually the first trend of the nucleophilicity. You follow me? This is always actually, whenever we talk about trends, actually in the periodic table, we always talk about in the same group and the same period. So the other trend here, when we go from the left side to the right side in the same period, or moving from left to the right in the same period, nucleophilicity decreases. Do you follow me? Always the nucleophilicity decreases this way, but increases this way. That's actually the two trends for the nucleophile. And the third trend, negative nucleophile stronger than neutral. In other words, if we compare, for example, OH minus as a nucleophile, comparing it to the H2O, which one will be, based on the same, will be definitely the OH minus is stronger than the H2O. These are the three trends for the nucleophilicity of the nucleophiles. Any question about it, about the nucleophilicity and the difference in the reactivity? Is there any question? Hello?
It's clear.
All right. But yani, I don't like it to be that much clear. Just some question, guys. Everything's very clear, very easy. Yani, just to make the lecture more interesting to all of you, if you have any question, please don't hesitate to ask. Any question, guys, before moving? All right. Okay, that's fine. Now let's talk about the leaving group, because part of the reaction or this reaction is the leaving group. So which leaving group is better leaving group compared to others? Here, the criteria to judge this is the basicity of the leaving group. So we're talking about now, we are discussing now the leaving group. Generally speaking, the weaker base, the leaving group the weaker base, the leaving group is better. Yani, when we compare two leaving groups, the one which is weaker base will be better leaving group compared to the other. In other words, let's just compare these leaving groups which you have it in here. For example, let me see here. The leaving groups here which we have it. For example, if we compare OH minus, NH2, OH minus, NH2 minus, suppose CH3O minus. If we compare the leaving capacity of these groups compared to the F minus for the halogens, F minus, Cl minus, Br minus, iodine minus, and what we call it the tussle, iodine minus. Now as you can see here, these atoms or these leaving groups are very weak leaving groups. They are very much less than 1 rate of reaction. If this is 1, this will be, the chlorine will be like 10,000, no, chlorine will be 200, the bromine will be 10,000, and iodine 30,000. 10,000, iodine 30,000, and this tussle group here, which is this group here, we call it tussle group. And this tussle group here, it has 60,000. Now, first of all, why we call it this tussle group? This tussle group here is very powerful, very good leaving group. And we call it tussle, and we abbreviate it by TS. That's actually the tussle group, how we abbreviate it. And why we call it tussle? Because the IUPAC name of this group, it will be actually coming from the toluene sulfonyl chloride, para-toluene sulfonyl chloride. Para-toluene sulfonyl, or sulfonate actually in this case, but anyway, sulfonyl chloride, sulfonic acid, para-toluene sulfonic, let's say just sulfonate. Para-toluene sulfonate. That's why we call it tussle group. Anyway, that's actually the difference in the reactivity. These groups, we call them very poor leaving groups. Do you follow me? The groups like OH minus, NH2 minus, any alkoxide like CH3O minus, ethyl O minus, propyl O minus, any alkyl attached to O minus will be very poor leaving group. Do you follow me? Because as you can see, the rate of leaving here will be very much less than 1 compared to the F minus, which is 1, compared to the Cl minus, which is 200. You see that this is way much higher than the fluorine, this bromine way much higher, iodine way much higher, then the tussle is the best in this case, which is the very powerful group. The criteria for the leaving ability is how weak the base is. As the base becoming weaker base, the leaving power or leaving ability will be better. Clear, guys? Is there any question?
دكتور،
Yes, please.
في ايش يستخدم الريت اوف رياكشنز؟ يعني في ايش يفيد؟
the rate of reaction هو زي سرعة التفاعل. Do you follow me? Here just comparison, just to compare. You follow me? Just to see which reaction is faster than the others. And this will give us indication about the leaving group, the nucleophilicity strength, something like that. Do you follow? The rate of reaction is the speed of the reaction, how fast the reaction will go. In other words, if we have the tosyl group as a leaving group, compare and we make the same conditions are the same, everything else is the same, what we will find that the reaction which has the tosyl will be 60,000 faster the reaction if it has a fluorine as a leaving group. Do you follow me? Did I answer your question? Yeah. The rate here, which we use it as indication of the preference of a reaction to go or not to go. All right? All right. Now,
يعني دكتور
yeah. Go ahead.
لما يكون الريت قليل كل ما كان إنه الليفينج جروب أفضل صح؟
لا، لما تكون الريت قليل كل ما كان الليفنج جروب worse. You follow me? يعني the best كل ما زاد الريت كل ما زاد الريت of reaction, that means the living group is better. You follow me?
بس بياخذ وقت أكثر.
لا، شو معنى ريت انه يكون شيء if something is very fast هذا هياخذ وقت اكثر ولا وقت اقل؟
أقل.
طبعا كيف بده يكون وقت اكثر؟ يعني بيكون الريت 60,000. What does that mean? When a reaction is 60,000, it's not 60,000 second or 60,000 minute, it's just comparison. You follow me? 60,000 times faster than 30,000 than the iodine, for example, which is 30,000 faster than the bromine. The bromine is 10,000. And if you compare the rate of the reaction of the tosyl to the fluor, this is 60,000 times faster than if we have a fluorine. The iodine is 30,000 times faster than if you have a fluorine. The bromine is 10,000 faster times compared to the fluorine. You follow me? Clear?
Yes.
All right. So this is here the indication for the ease of the leaving group. يعني the best leaving group is always the weakest base. يعني بمعنى أو بآخر كلما ازدادت ضعفت البيسيسيتي اللي هو قاعدية الليفنج جروب ازدادت سرعتها في المغادرة, becoming better leaving group in this case. As we have discussed before, the methods for preparation of the method or some methods for the preparation of alkyl halides. As we said before, we may prepare alkyl halides by two methods. One general method, which is simply reacting alcohol with thionyl chloride, and the other one reacting alcohol with phosphorus tribromide. See, some methods for the reaction of alcohol, of alkyl halides, or preparation of alkyl halides. If we have, let's say, alcohol, and we allow this to react, let me just take the specific example as you have it in the slide in here. Okay, suppose we have specific example in here. All right, okay. So here we have OH, hydrogen, methyl, and then CH2, CH3. Suppose, for example, all right? This will be secondary. Now, and then we allow this to react with thionyl chloride. In the thionyl chloride, the chlorine here will come with a retention of configuration. So hydrogen, and then Cl. This will be, sorry, there will be, yeah. SOCl2, no, at the final it will be inversion of configuration, yeah. Okay, inversion of configuration will be like this, C, Cl, and then hydrogen, and that's the same. CH3, CH2, CH3. In this reaction, for the preparation of the alkyl halide, we studied this before. We said this is one method for preparation of alkyl halides. Like what we want to highlight here is the stereochemistry of this reaction. Generally speaking, converting this alcohol to this alkyl halide, it goes via inversion of configuration. Inversion of configuration. We'll tell you if this is here for any reason, this is, what's the absolute configuration of this reaction here? This will be, we should check it from here. We will have like, this is S configuration. If this is S configuration, this must be R configuration. We tell you, anyway, what we want to highlight in here, that the chlorine here, which coming from the thionyl chloride, in this reaction will be always opposite or inverted position of the OH. We tell you, wherever the OH in here, it will be the chlorine becoming this side. So this is the product of this reaction. You see here, this reaction occurs with inversion of configuration. That's a very important aspect regarding the stereochemistry of the reaction. The same thing applies here when we allow it to react with BR3. It's the difference here, we will get a BR, but again, we will get it here, the carbon here, everything is the same, but the only difference is that the BR here will be, this here will be the hydrogen. So again here will be inversion of configuration for both reactions. This reaction or that reaction, we will have inversion of configuration. Take this into consideration, because if you allow now to react this with the nucleophile via SN2, then what's going to happen? Again, this here is always accompanied with inversion of configuration. So here we have R, for example. You see, we said this is R, right? What we are going to get that the S now, the nucleophile will be here in this side. Do you follow me? Like we have double inversion of configuration. In other words, if we started up with an alcohol with certain stereochemistry, we convert it to alkyl halide via reaction with phosphorus tribromide, we are going to get inversion of configuration for the alkyl halide. If we allow the alkyl halide to react with a nucleophile via SN2 reaction mechanism, what we are going to get, a nucleophilic substitution with another inversion, which means the R here becoming S again. That's actually very important aspect regarding the stereochemistry of the reaction. Any question? Is there any question?
No.
All right. So this is about the stereochemistry of the reaction. Let me see here. Let's talk about the influence of the solvent here in this case. Now, as you can see, what will affect or when a reaction will be faster, in which solvents? We can, generally speaking, we classify or divide the solvents into two types. We may classify them as polar protic and polar aprotic. So generally speaking, solvents can be classified into polar protic and polar aprotic. The meaning of polar protic, whenever we have, for example, oxygen, a solvent which has oxygen attached to a hydrogen, such as ethanol, for example, CH3, CH2OH. For example, water, OH. For example, any solvent like that. For example, amine. Any solvent like that, we call this polar protic. And the protic here, which means it has a proton attached to a high electronegative atom, such as oxygen or nitrogen in this case. That's actually what we call it, polar protic. Now, with a polar aprotic, there are a few examples. One of them is called DMSO and DMF and HMPA, hexamethyl phosphoramide, HMPA. All right. The DMSO, it's CH3 S double bond O CH3. This is called DMSO. And with that DMSO, it stands for dimethyl sulfoxide. Do you follow me? That's the structure of it. The DMF, it's simply C double bond O H N CH3 CH3. This is called NN dimethyl formamide. NN dimethyl formamide. And the last one is HMPA. HMPA اللي هو phosphorus double O hexamethyl phosphoryazine CH3 for a second. Hexamethyl phosphoramide. Yeah, it's yeah. All right. N methyl, and then N methyl. These are, as you can see, we call them polar aprotic. Polar aprotic. The meaning of aprotic here means there is no hydrogen, which makes the polarity. No hydrogen in this case. At the end of the day, what's for? Why we are interested in this division of these two solvents? Generally speaking, polar protic, they have ability to what we call it solvate negative and positive ions. Very important aspect in here. I will come to this. Now let's see what's the meaning of it. Let's talk about the polar protic and see what's their ability. The polar protic, again, their ability to solvate negative and positive ions. Yeah. But negative and positive ions. In other words, if you have, for example, a nucleophile in the solution and H plus in solution, and you have, for example, alcohol, ROH. This is the solvent. The solvent in here is what? Polar protic. Right? Now the polar protic has two ends. It has partial positive end and partial negative end. The partial positive will surround the nucleophile. So this will be surrounded by ROH from this side. ROH, R here. HOR from this side. And so on and so forth. You follow me? That's actually what we call it the solvation. Similarly, the other part here, H plus, will be surrounded by the negative part اللي هو our partial negative part. هيكون O minus HR, and this is here partial negative, and O minus, sorry, OH R, and then partial negative, and so on and so forth. OH R partial negative. Sorry. Do you follow me? Is that clear, guys? The polar protic, what's its ability? The polar protic solvents, they have the ability to solvate the both ions and the cations. You follow me? How? Because the polar protic, they have two poles, they have two ends. One is positive, one is negative. The positive will surround the negative, and the negative will surround the positive, because it's all about attraction forces. Clear? Is that clear, guys?
Yes, doctor.
Alright, so that's actually the main criteria of a solvent, which we call it polar protic solvent. Examples for that are water, ammonia, alcohols, all of these. Or in other words, any solvent which has a hydrogen attached to electronegative atoms such as oxygen or nitrogen. All of these we call them polar protic. طيب, what we need it for? Imagine this case, if we want the nucleophile to attack, as you can see, this solvation, when the nucleophile is hindered by the solvent, by the positive part of the solvent, it will be like it is hindered. It is somehow cannot reach the position of the reaction easily. That's why, generally speaking, SN2 reactions are lower in reaction in polar protic solvent, because, let me just write it. Generally speaking, SN2 reaction is slower in polar protic solvent, because the nucleophile will be solvated. The meaning of solvated will be surrounded by, of course, طبعا هتكون positive part or end of the solvent, and therefore its ability to reach the reaction center will be less. That's why, generally speaking, SN2 reaction are very slow or slower in polar protic solvent. And that's what's the difference between polar protic and polar aprotic? The polar aprotic solvent, on the other hand, the polar aprotic solvent generally, polar aprotic solvents can, yes please.
Can you please move the board
Can I what?
to the left?
Yeah, sure, sorry. This one, this side?
Yes.
Okay, now the polar aprotic solvent can solvate most likely or effectively the cations and not ions. The cations are not an ion. In other words, an ion or negative ions are free, or negative ions are not surrounded, are free, let's say. بالتالي, as you can see here, in any nucleophilic substitution reaction in SN2, we need the nucleophile to be free, to be able to reach the reaction center. If this nucleophile in this solvent, in this polar aprotic solvent, cannot be surrounded, it's free, then its ability to reach the reaction center will be higher, and therefore the rate of the reaction will be always higher. Therefore, in the SN2 reaction, I will just erase this, will be now faster, is faster in poorer aprotic solvents, solvent, such as, for example, DMF, DMSO, HMPA, and so on and so forth. Because, as I said, because the nucleophile is free in solution, or will be free in solution. And therefore, it will has better ability or higher ability to reach or to react with the reaction center. Is that clear, guys? Is there any reaction? Is there any question? All right. Now let's talk about the SN1 reaction mechanism, and then we'll stop at this point. But let's just make a very quick introduction to SN1 reaction mechanism. So we have discussed all the factors affecting SN2 reaction mechanism. So we'll go now to SN1 reaction mechanism. SN1. And in the SN1 mechanism, from its name, it's monomolecular. In other words, the rate of the reaction, the rate is only depending on the substrate, Rx. It has no dependence of the nucleophile. So it is first order reaction. This is the first aspect of the SN1 reaction mechanism. Second aspect, it involves formation of carbocation, and thus if there is something called racemization, it will, and thus racemization. Okay, so we will explain this when we now show the reaction mechanism in this case. And these are the most important aspect of the SN1 reaction mechanism. So there is a formation of carbocation, and it is a first order reaction mechanism. Let's take an example. For example, here we have carbon attached to, of course, 4 bonds. One of it is the halogen. Suppose Br. And then the reaction mechanism, the first step will be first the movement or the breaking of the bond between the carbon and the halogen, and then a formation of a carbocation. In this case here, there will be a plus. Do you follow me? First of all, the first step will be breaking up the bond between the carbon and the halogen, and then finally the nucleophile here, which will be presenting in the solution, will attack, and then we will have simply back the tetrahedral structure. Do you follow me? That's the mechanism of the reaction. The mechanism of the reaction, as you can see, the first step will involve it will involve breaking up the bond between the carbon and the halogen. You can see here, for example, this is the model. Now, in the SN2 reaction mechanism, the nucleophile attacks and this starts to move. بمعنى bond making and bond breaking happening or occurring at the same time. You follow me? That's why actually we call it SN2. It's bimolecular, depending the rate of the reaction depends on the concentration of the alkyl halide and the concentration of the nucleophile. You follow me? But in the SN1 reaction mechanism, then this nucleophile, its rule is postponed, will be later. The first rule, suppose the halide is the red one here. The first thing here this bond will be breaking up. بمعنى the halogen will take the bonding electrons which was with the carbon will go away. In this case, what's remaining is carbon having a positive charge. And in this case, as you know, in this case, when the carbon carrying a positive charge, the hybridization of the carbon will be sp2 hybridization. Therefore, it becoming like planar system, like this. You follow me? Now, the nucleophile, this now, at the second step now, it will attack. Now there are, as you know, in the sp2 hybridization, we have two loops here. This p